Hello, ladies and gentlemen. Good morning. Thank you for joining this seminar hosted by Keysight. My name is Koo. I work for Keysight Singapore. I wish I could join you in this fantastic event, but I think for this year's event, I'll just be presenting to you remotely. So the topic for my session today is going to be focusing on ORAN Alliance Working Group 4, mainly on the open front hall aspects. Any questions, comments you have, just let me know, please. So I lead the Keysight delegate team into ORAN Alliance, and I'm as well a director of technology for Keysight, focusing on 5G and OpenRAN. So for the proposed agenda for this session, I'll be spending some time with the team to look at the ORAN Alliance standards and the ecosystem, just maybe 1 or 2 slides on what Keysight basically does after the good introduction that Kobe has done. And then to spend some time to get the team maybe up to speed on the open front hall technology overview. And, I wanted to spend some more time spending going through the details of the case studies on how our customers and our partners today are using Keysight OpenRAN test tools for lab testing optimization, again, focusing on the open front hall aspects and getting into some of the conclusions and key takeaways. Perhaps just one slide to talk about what Keysight does within ORAN Alliance. As Kobe has mentioned, Keysight is very active. In fact, we started off with XRAN Forum, which basically got merged into ORAN Alliance. We are the first test and measurement vendor to join ORAN Alliance since its establishment in February 2018. And we lead basically the conformance test specifications in Working Group 4, focusing on open front hall. Now looking across ORAN Alliance, Keysight has basically invested our expertise into enabling the global ecosystem within the ORAN Alliance, which right now have 29 operators and 300 members companies. Myself, I'm the co-chair for MVPC, which is basically a new initiative within ORAN Alliance that will look at, devising, designing the ORAN Alliance activities and standardization plans, meeting the industry and operators' needs. We are a member of technical steering community, basically with the oversight across all the work in ORAN Alliance. And with Keysight, basically our delegate team focuses on all aspects of ORAN. That includes the RAN intelligent controller for the non-real-time break, near real-time break. We are basically a management plane contributor, right? Basically the O1 interface that does all the smart orchestration of the entire ORAN network. Including cloudification and orchestration for Working Group 6, transport. We're going to touch on some of these aspects later on because it's a critical element for front hall to be working correctly with performance. Security, a very important aspects that we'll be focusing on within ORAN Alliance, and obviously the test integration focus group. So in a nutshell, Keysight is really committed to enabling the entire ecosystem, and we are basically driving and leading the work in ORAN Alliance across all components from conformance, interoperability, end-to-end. And there's a new term as well, maybe OTIC certification and badging that we'll try to spend some time on it later in the presentation. Spending some time to get maybe some of the audiences up to speed on, when we speak about open front hall, what does it cover? So open front hall compliance, basically to industry cover 2 things. One is basically a 3GPP compliance, and the other aspects is ORAN compliance, right? So everything which is supported by 3GPP radio access network today, that includes what Kobe has mentioned, right? ORAN is very focused on optimization for 4G LTE, 5G new radio, FDD, TDD, right? Frequency range 1, range 2, and including, key features like dynamic spectrum sharing. Right, the OpenRAN aspects would actually be applicable for internal to the radio access network, but towards the device and towards the core network is basically 3GPP compliant. As such, all the standards which are basically required within 3GPP to be validated, like for example, the eNodeB, GNodeB conformance and performance test, and as well as the security assurance specification, right, which are basically applicable for any 3GPP RAN, including the single vendor RAN, would be applicable for OpenRAN as well. MIMO, massive MIMO is definitely supported within OpenRAN. We are basically supporting our customers today in terms of optimizing their massive MIMO multi-vendor setup, up to 64 TRXs, supporting multi-user MIMO, up to 16 layers in both directions. So this is one of the main, it's kind of like, it's an initiative at the moment within the OpenRAN framework. In terms of beamforming, grid of beams, non-grid of beams, analog, digital, hybrid, all forms of beamforming. We have one slide that touch on the details later, and deployment scenarios with indoor small cells to outdoor massive MIMO, anything in between. The ORU ODU for macro networks can be deployed 20 to 30 kilometers apart with switches and routers in between, and we'll look at some of the implications that you'll be creating for the open front haul interoperability. And the ORU ODU can be deployed as a standalone network function or basically within a combined node that will look at some of the implications and challenges for interoperability soon. Now, when we start to look at within the OpenRAN, on the right-hand side, what you see is that I have colored the blocks in terms of what are the key devices under test. Obviously, from a open front haul perspective, you start to look at the ODU with a virtualization running on top of the old cloud infrastructure, and then it's connected to the ORU over the open front haul interface. There are basically two modes of management plane for the open front haul specified, the hierarchy and the hybrids. We'll spend some time on it later on in one of the slides. In the hybrid mode, the SMO, basically the service management orchestrator, this is like the ORAN orchestrator that's going to be communicating to the ORU, managing the ORU as well, together with the ODU. And then the ODU and ORU obviously is actually connected using the transport as a service. So when we start to look at multi-vendor interoperability for the open front haul, we look at the functional, performance, and security aspects of it. And obviously, as I mentioned, the open front haul, the interoperability between the ORU, ODU across all the planes, right? Over here, we talked about CU, SM plane. These are really important, but at the same time towards the SMO for the management plane. With the transport infrastructure, right? We have actually seen in testing, both in the labs and field deployments on how transport performances may actually impact the open front haul interoperability. The virtualization aspects with the VODU running on the old clouds, and how do we actually test and optimize with close to real world RF conditions. And on the transport perspective, what is actually really interesting is that the latency figures, which are basically imposed on the transport nodes, switches, and routers, the latency will vary between 25 to 200 microseconds. It really depends on the services that you're trying to run. For ORAN, like for example, when we start to look at industry IoT applications, for ultra reliable low latency, it's a one-way latency, could be down to 25 microseconds over the open front haul, which otherwise the ODU and ORU would actually fail to communicate to serve the needs of the applications, and obviously jitter packet losses. In other words, the transport nodes will need to be, tested for performance, interoperability, and you will need to make sure that we can simulate some of this real world scenarios within the lab to really validate the interoperability of the open front haul between the ORU and ODU. Last but not least, in terms of virtualization, as I've mentioned, I'm going to share some case studies on how our customers, some of them, they are basically supplying the old clouds into the ORAN ecosystem. They are basically testing. We look at how they test the old cloud, how do they actually test with their partners, having their partners ODU to be running on their old clouds, and vice versa. On slide number 6 right now, this is a listing of all the Working Group 4 specifications that has been most recently announced as part of Mobile World Congress Barcelona. And you can download all the specifications using this link here if you don't already have it. So Working Group 4 basically provides technical specifications for control, user, synchronization, and management plane. Right now, everything's on 6.0, including the Young models. So the management plane uses netconf Young. And it as well provides conformance test specs. So Working Group 4, again, we are part of Working Group 4, working very hard together with our partners. We develop conformance test specs, right? We're cover some more details on what we mean by conformance test specs to make sure that every single subsystem like ORU, ODU is actually tested to the last level of details from a conformance perspective, and then interoperability for ORU and ODU. And then from the one other group basically is called the Test Integration Focus Group, and Keysight has contributed significantly to the certification and badging processes, right? So what this means is that the certification badging processes is like when you go to college, you get a degree, you get a diploma, right? For network functions like ORU, ODU in the context of Working Group for Open Front Hall, you can basically go to these places called the OTICs, the Open Test Integration Centers, and get the certificates. With the certificate, you'll be able to go to different operators, right, customers, and say, hey, by the way, my ORU ODU has been tested against this conformance interoperability test specifications based on these capabilities, and you will get recognized by the operators and as well as the industry. And there's as well end-to-end test specs along with the badging for end-to-end. Okay, this is really to make sure that the ecosystem would have confidence, and it helps to accelerate the OpenRAN adoption and deployment. I'll cover a little bit in terms of like the technical specs. I'll go to the test specs from the technology overview perspective. Because these are the functions that we support today within our Keysight test solution. So I wanted to give you a flavor in terms of the complexities involved. As Kobe has mentioned, so ORAN Alliance Open Front Hall in Working Group 4 has adopted what we call the option 7.2x. This is not standardized within 3GPP. This is an innovation within ORAN Alliance headed by Working Group 4. And option 7.2x, there are multiple lower layer splits that has been previously discussed in 3GPP. And 2x basically take the split between the phi high, phi low. To be specific, is basically a cut in between the resource element mapping and the pre-coding. So there's some differences in terms of the pre-coding, right? Because we have defined two categories of ORU within the Working Group for Open Front Hall specs. There's a category A, which is basically without pre-coding. This is simple, affordable, and we've actually seen this deployed in the first wave deployments commercially in the industry. So what this means is that you basically do the pre-coding within the ODU, and you send the pre-coded streams, what we call the spatial streams, into the ORU. So the old ORU is now very simple, it's very affordable, and you can actually deploy the ORU without a lot of impacts, right, in terms of cost and complexities. But at the same time, it does actually increase the loads of the front hall interface, because when you start to look at the sending the spatial streams, right, basically you're increasing the number of data that needs to go across the front hall in the downlink direction. Category B basically is a new generation of ORU. It's more ideal for massive MIMO implementations, especially for frequency range 1, sub-6, sub-7. It has pre-coding basically within the ORU. So the ORU now is more complex, it's smarter. So in this case, right, the ODU would just send the data layers. So the pre-coded input layers instead of the spatial streams. So you decreases the front hall throughput significantly, right? And then it supports the modulation compression as well, which further reduces, right, the capacity requirements on the downlink. So the main difference here is really in terms of the downlink. Uplink is basically pretty much the same. The key takeaway here is that when we start to look at interoperability and testing, right, obviously the ORU may support either category A or B, right? It got to be optimized for one of them depending on the deployment scenarios. ODU though, when you test the ODU, it must support both category A and B, right, up to 8 spatial streams of pre-coded outputs according to the specifications. Now, we look at the beamforming methods. There are 4 beamforming methods in general specified within Working Group 4 specifications. And what's actually really important is that when you start to look at multi-vendor interoperability for massive MIMO beamforming, a very important criteria is to be able to match between what the ODU and ORU supports, and they have to be tested independently. And when you put them together, they have to be optimized for each one of them. So for the grid of beams, right, this is basically a static beamforming scheme. The ODU will pass the beam index to the ORU. It's like, OD would say, by the way, beam ID 1, this is what you need to do. ORU would have a lookup table, and you will select, right, okay, these are the weights associated with the index. With 2, this is non-grid of beams. Basically, it's weight-based. So OD would send the real-time updated digital weight calculated within the ODU to the ORU, right? So ORU just say, okay, these are the weights pre-calculated for you. For each of the TRXs and IQ, just use it, apply it to the user plane data. You have attribute-based. This is where you start to look at the ODU sending the ORU in terms of the beam forming azimuth, right, zenith, phase, beam width. So everything that you need to be able to form the beam, but then the ODU basically will generate the weights. And then the fourth one is quite complex. Basically, you send the channel information and the UE scheduling information, and the ORU would generate the weights as well. So within Keysight, we have actually seen multiple all these schemes getting implemented and obviously specified within ORAN Alliance. We're supporting our customers in making sure that their massive MIMO for the beam methods they have actually selected to implement are basically optimized. Getting to the protocol stack a little bit, there are 4 planes are specified. So this is a diagram, a picture that we put together in terms of how this works. So the common layer here is basically what has been specified within working group 4. You would have the control user plane, the synchronization plane, and the management plane. For the control plane, basically it is running on top most commonly over eCPRI. Radio over Ethernet is specified as well, but it's not very commonly used. And the 3GPP protocol stack would actually run on top of the U plane, which is operating over frequency domain IQ. The FILO, as we have discussed earlier, would actually reside within the ORU, and the PHY high, the MAC, and the RLC is actually designed to be running within the ODU. So control plane, as the name suggests, right, basically is used for coordinating real-time communications between the ORU and ODU, and is used to be able to communicate, like for example, what are the beamforming rates to be used for the user plane transfer, right, between the ODU and ORU. User plane is frequency domain IQ. This is 3GPP data, payloads in uplink and downlink. Working group 4 has defined 4 synchronization topologies. We'll have a quick look at them quite soon here. And then in terms of management plane, it's very important because when operators start to look at deploying an ORU, they want to be able to manage it. They want to be able to make sure that in terms of configuration management, performance management, fault management, everything is taken care of. And there are 2 modes that's been specified within working group 4 for ease of deployments from the operator perspective, because the deployment models are quite different in some cases. So for Seaplane messages and U-plane messages, it's actually very important that we look at how they work together, right? So as we mentioned in the previous slide, U-plane would carry the 3GPP protocols, and the Seaplane messages would actually be used to share with the ORU, both in the uplink and downlink direction. So the figure that you look here is in the downlink direction. The ODU would basically send a C-plane message and say, well, for all this U-plane message that needs to be transmitted for symbol 0123 over slot 012. So these are basically the air interface, a time division multiplexing information that you need to be sent across the air. So the C-plane message will basically contain the information that you need to be able to apply over the U-plane message, especially on the 3GPP payload, right? So that's really important. So this has to be coordinated. And for coming back to the massive MIMO approach, right, or the massive MIMO beamforming methods, remember, we talked about category A and category B. So in terms of category A, the U-plane would actually carry the spatial streams because the pre-coding is actually being performed within the ODU. And then here, in the case of category B, the U-plane will carry the data layers because the pre-coding is performed within the ORU, right? So this is just mainly used as one example, but obviously for the CU plane, there are more variants, right, in terms of design and implementation. This is a very key feature that I'd like to spend some time on. So when you start to look at disaggregating the ODU and ORU, which means that you'll be physically apart in real world deployment scenarios, right? So it's not like in the lab, you basically have a straight fiber connection that you connect the ODU and ORU with a close to zero delay, especially if it's actually a fiber. And you don't actually expect much of a packet loss and jitter. And in the real world scenario, it's not like that. So working group 4 within the Open Front Haul specs has actually designed in a key feature. It's called front haul delay management. It's being implemented within the ODU and the ORU. So this picture, right? We basically references from one of the very good journals that was published by Docomo. It's a public reference. The ODU would actually have a processing delay, right? And then you will start to look at the implementing. So within the ODU and ORU, you would actually have a transmit window and receive window. So as we discussed, the control plane message would need to precede, right, send before the U-plane message, that the ORU would know what are the control plane parameters, right, to be applied for the 3GPP payload to be sent across the air interface. So the ODU would have its own processing delay. You will have a transmit window. So anytime within the window, it can send out the packet. For Seaplane and U-plane, you have to send the Seaplane before the U-plane. And within the ORU, you basically would actually have a receive window, and as well as the ORU processing delay, right? And obviously you would have the front haul delay. So these are the transport node delays and stuff like that added by your switches and routers. The key thing to make sure is that the transmit and receive window are basically tied to the ODU and ORU implementation because there are internal memory buffers associated with the ODU and ORU, especially the ORU is not designed to hold minutes of data. So the timing has to be extremely accurate to make sure that anything that was actually sent in the downlink or received on the uplink, right, has to be synchronized very, very carefully, just to make sure that the air interface or the packets, right, that's supposed to be sent out to the devices and received on the devices in the downlink and uplink respectively, can be sent and received on time and correctly. So this is an extremely critical feature to be tested and making sure that it's actually well optimized, which otherwise for an open front haul would not work. So a few things that we need to be able to look at is that the front haul delay is really topology dependent and subjected to variations like the live networks, right? The distance and the switch processing delay. And the ODU, ORU, basically they're subjected to matching, right? You need to be able to look at matching ODU and ORUs of this, similar delay categories and delay subcategories as specified in the open front haul specifications. And Keysight, I'll go through some case studies on how our customers are basically using our test setup to simulate this in the lab, to bring the field conditions back into the lab to test before you deploy and test in the field. From a management plane perspective, we have basically looked at the obviously all the functions which are needed, right, to deploy the ORU, including installation, software configuration, performance, fault, and file management. What's actually important here is that there are two management plane deployment topologies specified. Hierarchical, which basically manages, so if you look at this figure here, maybe it's clearer. The SMO or the network management system within the SMO would actually connect to the virtual ODU or the ODU over the O1 interface. For what's actually concerned of the open front haul, the ODU will run a netconf client, and the ORU would always have a netconf server. And basically, from ORU perspective, it's actually being managed by the ODU. In the hybrid mode, you basically would have two routes of management. You get a netconf client running within the ODU, and as well as the SMO, and the ORU would still run the netconf server. So there are different advantages of each one of them. With hierarchical mode, basically you can speed up the ORU deployments. not needing to upgrade the existing infrastructure, as in the SMO, or you don't actually need to deploy SMO to deploy ORU with hierarchy mode. But with hybrid mode, basically you need to make sure that it can upgrade the SMO to manage the ORU. For synchronization, this is extremely key, obviously, especially not just for ultra reliable low latency services, but just for communications to work in general, especially when the ODU and ORU, they are designed to be disaggregated, separated physically, and maybe up to 30 kilometers apart. So C1 is the simplest configuration, whereby the grandmaster, the synchronization grandmaster is running within the ODU, and the red color, basically the arrow represents the synchronization path, right? These are basically when the PTP signals are being sent to the ORU. This is the simplest. We've actually seen most commonly implemented in the network, the LAS C2 and C3. C2 basically involved, you would actually have switches and routers in between, right? Still, the grandmaster is still within the ODU, but now you would actually have to make sure that the PTP signals gets sent correctly to the ORU. C3 basically involved the grandmaster, so maybe one of the switches like the TBCs would actually be one of the grandmaster, and you start to look at distributing the PTP signals towards the ODU and ORU. And configuration LSC4 basically applies when you have one or more switches within the front hall that's actually in the path of the front hall does not support PTP signals passing, so you will synchronize the ORU to GPS. And the ODU can decide whether you want to be able to take its own clocking source or through the ORU through other routes. But it doesn't change the fact that the ORU and ODU in any of the configuration must be synchronized, in a very tight fashion. So when we look at multi-vendor interoperability, ORAN Alliance has designed a few approaches, right? Basically, they're working together for testing to make sure that every single component can be tested. So the whole thing is actually designed to support continuous integration, continuous development, and continuous testing. So the idea is that in this case, for a open front hall, the ORU and the ODU will need to be tested in isolation, right? So the blue boxes will indicate the device under test, and the red boxes, these are basically the test tools which are provided by Keysight. We'll spend some time on some of the details later on. But what this means is that for ORU, you basically would need to perform a complete wraparound, right, to test the ORU in isolation using the vector signal analyzer generator, the ODU emulator, and then making sure that you can actually connect to the ORU with the SMO emulator if it's actually operating in hybrid mode, as we discussed earlier. In the case of ODU, basically you will need to be able to emulate the ORU and the rest of the components together with the UE emulator, so that you can actually test the ODU based on 3GPP protocols as well. On the interoperability testing, this is when you've actually test your ORU and ODU in isolation. They pass all the tests for conformance and subsystem testing. You start to look at testing them in pairs, right? So you look at, you basically look at having the UE emulator to be emulating a lot of UEs, and then connecting to the ORU over the RF interface, either using conducted mode cable connection or over the air. And then after that, the ODU as well is the device under test with the backend connected to a OCU, a core network, and SMO emulator. Once you have actually tested the device under test for conformance interoperability in isolation, in pair, respectively, you start to look at testing everything within the system for the labs and fields. So the whole ORAN, right, components is basically the system under test. And again, for conformance tests, basically we will start to look at applying certification process, so it can be awarded a certificate if your device passed the conformance test. The same would apply for interoperability, for OTIC badging, and then for system test, that will be OTIC badging end-to-end test. Getting a little bit into what Keysight basically does for our customers in the ecosystem. So this chart I'm actually showing here basically have a lot of significance when we start to look at applying our knowledge, our expertise, and our test tools to support open front hall testing. I've colored them in red here. Basically, we supply test tools that goes across, starting from a pre-silicon testing. So Keysight, basically, we're helping some of our customers who are developing their chipsets for the ORU and ODU to test their design for the open front haul before they implement their design in the ASICs. And we basically test, obviously, the ORU, the ODU, the front haul transport in terms of the routers and switches, and the cloud computing servers, which are basically being used to run the ODU. And this is a list of sample customers that we have here. I'll get to some of their case studies very soon here. For the OpenRAN test tools, one of the key focuses that we look at is that Keysight, we have launched our OpenRAN Architect solution is the Cora to support conformance subsystem interoperability and performance testing for all the ORU, ODU, OCU, and the rigs. Right, this is basically a set of test solutions which focuses on ORAN internal testing. And then to support ORAN testing, we basically applied our expertise, our tools for RF millimeter wave testing, conformance testing, and my colleague will cover the S-NIFR aspects of it, which is a very significant portion of the testing, right, when we come to OpenRAN testing and 3GPP RAN testing. And then for the radio channel emulation to make sure that we can inject impairments, and as well as making sure that we can test the ORU and ODU with real channel emulation, like close to real world conditions. The corner network emulation testing solution is to make sure that the corner network by itself is robustly tested before you start to look at putting the RAN and the core together for system testing. And the testing the ORAN as a system under test in the end-to-end system testing with our RAN testing UE emulation framework that is capable of emulating thousands of UEs and lots of cells that we can try to stress test the ORU, ODU, and OCU together and the rigs, and then the core emulation to make sure that the RAN can be tested in isolation. We as well have test tools that right now we're basically helping our customers to install ORAN solutions, benchmark, and for site acceptance using our FieldFox and Nemo test solutions in the field. And very importantly, ORAN, as we've mentioned, it has to be tested for security, right? The ODU, OCU running on the cloud, the transport that's going to be impacting the front haul performance, and timing synchronization. And the whole framework is being supported by our testing automation framework, for the CI/CD CT approach and RAN analytics to enable network automation, which is a key part of OpenRAN. So spending some time on some of the case studies. So this slide that you're looking at here is basically for ORU testing. Is the industry only integrated ORU test solution. This solution is called the OpenRAN Studio. What this does is that we basically apply our signal generator and signal analyzer that's connected to the ORU. So the blue boxes, these are the device under test, and the red boxes, these are basically what the test tools is emulating from Keysight. And the ODU emulator is being implemented in OpenRAN Studio. So between the ODU emulator that we implemented and the VSA VSG, this requires seamless test coordination. And the reason why I say that is actually because if you remember what I've actually shown you in the earlier slide, to be able to send a downlink signal over the air interface, we got to make sure that the ODU emulator would be able to send the control and user plane over the open front haul, and the user plane basically carries the 3GPP payloads in a time synchronized fashion, making sure that the delay management is actually operating correctly, implemented within the ORU in this case, so that we can actually receive it over the downlink in the VSA. Similarly, before the VSG is actually sending a signal up in the uplink, we got to make sure that the ODU sends a control plane over the front haul interface, so that the ORU would be able to pass the information over the open front haul interface to the ODU emulator for validation. So this is a complete solution that will support 3GPP conformance testing, ORAN front haul testing for control user synchronization management plane, including performance measurements and validation. And we have customers right now basically using this test setup to evaluate how the ORU they're designing can be applicable for private networks, industrial IoT, and getting some of the spacers in terms of energy savings management for ORAN. And obviously, as we discussed, right, we are right now basically supporting our customers for indoor small cells testing for the ORU, and as well as massive MIMO for frequency range 1 and range 2. Frequency range 1 mainly for digital beamforming, and range 2 getting to the analogs and in some cases hybrid beamforming. So apart from looking at testing, right, so we test the ORU, but we want to make sure that when there are issues which are basically surfacing from the testing, how do we help our customers troubleshoot, right, interoperability issues? So over the UU interface, we apply the air sniffer. This is our wave charge product that my colleague will cover in more details quite soon here. That we can get all the visibility that includes the IQ signals and as well as demodulation all the way to the control user plane for the 3GPP stacks that give you complete visibility of the air interface. So now when we start to look at if there's going to be interoperability issues, right, for conformance testing, when you start to look at testing the ORU over the front hall interface, we basically apply the Keysight protocol analyzer, we call the front hall analyzer, over the OpenRAN interface that we can start to look at if there are issues related to control, user synchronization, in some cases management plane. Then these are the possibilities that we can try to look at. So we cover both the air interface sites and the front hall protocol analysis sites, and alongside with our cloud visibility solution, right? If your ODU is running on top of an old cloud, then there will be cases whereby the packet brokers and the cloud lens will be applicable to get you additional visibility. So we cover test and visibility within one integrated portfolio. Then we spoke about how do we actually make sure that we can test the ORU not just from a functional perspective. In this case, you need to be able to make sure that you can create channel models which are very close to real-world conditions, because the ORU is not just designed to operate in ideal environment. We basically apply a product that we have. It's called the PropSim Solution, right? That basically gets connected here to the ORU, that we can actually have realistic channel models emulated. We can performance test the ORU. This one is a new product that we are launching very soon here. Remember, we spoke about the open front hall interoperability that talks about the transport, open front hall transport delay variations, right, for the delay management. With the network emulator product that creates impairment, we're able to look at injecting delays, jitter, packet loss for all the packets in the uplink and downlink. So without this product, basically what you're looking at is that having the ODU and ORU to be connected using straight fiber would get to close to zero latency. But when you want to be able to look at the, testing the ORU in cases that exercises the delay management feature for up to 20, 30 kilometers with switches and routers in between that we know will be inserting some of this realistic impairments, then this is what when we apply the transport impairment generator into this network. And transport impairment in terms of like the validating the delay management feature is a requirement to receive, right, the OTIC certification, right? So this is really key to make sure that you can actually inject impairments, right, close to real world conditions over the air interface and the transport interface. And the whole framework is obviously supported by Keysight's test automation engine. And as I mentioned early on, the reporting framework to make sure that all the test results are reported and enabling network automation. Now we have examined some of the use cases on how our customers and partners are basically testing their ORU, and now let's try to look at the ODU, right? This is a case whereby the device under test is the ODU. We have the Keysight ORU emulator. We call this the RU Sim product. And it's a very unique product because now we are looking at testing the ODU by connecting a software that runs on commodity off-the-shelf server that's connecting to the ODU over the open front hall interface, right? 1025 gig E, EC3 link, and there's no complex RF connection. But within this product, we are capable of emulating many cells and many UEs with mobility patterns that can be applied to these UEs, combining the collective knowledge that we have within Keysight that includes the channel modeling aspects, the UE sim aspects and as well as the Nemo aspects, right, the test UE aspects, so that we get all this information included within the ORU, that we emulate the ORU and we emulate the UEs behind it to be able to perform meaningful conformance subsystem testing for function and performance on the ODU. All right. And then if this ODU is actually being implemented as a standalone ODU, we have an OCU emulator that terminates the ODU. If it's actually a combined ODU OCU unit, you do not need to apply the CU sim. And we have a core network emulator that operates either in the NSA, SA mode or 4G EPC to be, basically supporting the ODU testing. So this is a very sophisticated testing product on the RU sim that we have implemented within our solution portfolio. And similarly, we apply the protocol analyzer for front hall analyzer to be able to troubleshoot, any interoperability issues that may occur over the open front hall interface, and our cloud and network visibility solutions that include the packet brokers and the cloud lens into this test setup here. So the common set of test tools being applied for ORU and ODU testing for actionable visibility, and as well as the test automation framework and the RAN analytics reporting framework. So maybe spending a few more minutes on the cloud testing because I think I'm running out of time here. As I mentioned, right, it's really important to make sure that the cloud can be tested to ensure that it can actually sustain the requirements of the workload, the ODU in this case running on top of the cloud. So we apply a product called a Cloud Pick that basically looks at comparing the infrastructure of the cloud, optimizing the configuration, identify bottlenecks, and planning for capacity for the old cloud to make sure that when you start to look at, operating the ODU over the old cloud, you will not run into any challenges, right, when you're starting to look at validating the open front hall that's created by incompatibility issues between the ODU and the old cloud. And then the transport testing for all the layer 2, layer 3 testing using our IX network product to make sure that the link speed, line rate performances are tested. We do EC simulation and performance load testing as well, along with the PTP transport switch functions and performance load testing. If you remember the 4 or the, I think there will be like 2, right? Especially for LS C2 and C3 and C1 configuration that's to be tested because the PTP signals are basically transferred across the open front hall interface. And from the these slides, I will just skip them, right? Because the same methodology or same tools will be applicable for end-to-end system tests as well. Okay. And maybe a concluding remark. I would say, we have, myself, I've actually been working on the ORAN and Open ORAN Alliance for the past few years. We're seeing that OpenRAN is gaining a tremendous momentum with key challenges needing to be overcome. So Keysight has been working with our partners within the global OpenRAN ecosystem for many years, supporting our customers with a comprehensive OpenRAN test portfolio. We have expertise basically across all parts of the OpenRAN ecosystems. That includes the radio, RF, millimeter wave, the radio access network, full stack expertise, the lab field testing expertise in terms of transport, timing synchronization, clouds, and as well as we offer test as a service in cases whereby customers are basically needing our advice, right, in terms of like how do we participate in standards, how do we design the test cases, where do we deploy ORAN, how do we design it in standards collaboration within ORAN Alliance 3GPP, and we explore with our customers how do you actually apply ORAN, for example, in some cases for industry IoT, private networks applications. Keysight today, we have actually partnered with all parts of the ecosystems. That includes the chipset, the radio access network suppliers, and as well as the cloud suppliers, the switcher suppliers, and as well as the industry IoT players, right? Basically fostering an ecosystem that we look at the, just collaborating and booming the ecosystem. And last but not least, I would like to say that the ORAN test solution portfolio from Keysight, we basically provides a holistic solution throughout the entire OpenRAN network lifecycle, from research, technology evaluation to network operations. So with this, I'll just conclude my presentation, and I'll take any questions and comments later. Thank you.